Thanks, Anna. Hi, everyone. Okay. Can you hear me now? Okay. Well, good morning. Well, good afternoon. It's right after 1.
Sorry, you need to kind of swallow the mic.
Okay. Hello, Mike. I write a lot of Python code, and I am a software engineer living right here in San Francisco. You may know me from these other places on the internet, and today I'm going to talk about HTTPS. Before we begin, let's look at some code. This code is trying to safely open a URL, and it's passing some secret as the data. The URL has HTTPS in it, so this looks secure, right? HTTPS does stand for HTTP secure, so we should be all set, right? Well, you would think that, but depending on the version of Python you're using, this code can be really, really insecure. It could be almost as bad as not using any encryption at all. Ready-made spoofing tools on the local network can steal the secret with a man-in-the-middle attack. The problem here is that URL-lib2 is I would have said will, but may not validate SSL certificates at all in this case. Python 2.7.9 supports TLS validation, but before that there was no support for it at all. And for a while, it was not even on by default. So the developers had to actually go in and flip the switch on. So if you didn't know that you had to validate SSL certificates for things to be secure, which it should be on by default. It wasn't way back. We will come back to that code and try to look at it more. But before that, let's talk about the types of attacks against any kind of communication. There are passive attacks that only need to be able to listen to the communication without injecting or rerouting. For example, a crypto flaw might allow an attacker to just read your encrypted traffic and decrypt it silently. Active attacks involve sending data to either party or misdirecting traffic. This usually takes the form of a man-in-the-middle attack. TLS is largely not vulnerable to passive attacks, though there's always the possibility. Before we learn more about TLS, let's learn a bit more. Well, let's actually go to a disclaimer. Here are some facts. SSL is secure sockets layer. TLS is transport layer security. SSL is old and busted and shouldn't be used anymore. The last release of SSL 3.0 was in 1996. TLS 1.0 was released in 1999. And TLS 1.2, the most recent version, was released in 2008. So TLS has superseded SSL. Do not say SSL, even if what you really mean to say is TLS. Okay, back. Most of this talk is about TLS. Because HTTPS is just HTTP on TLS, and I think, people would hardly come to see a talk if I said comedy of errors in TLS. So, HTTPS. TLS was designed to secure TCP connections. There are two aspects to actually doing the securing. There's authentication, and there's encryption. Certificates are used for authentication. It allows us to identify a peer. Without authentication, encryption is pretty useless. It's like picking up the phone and verifying the identity of the person on the other side of the line before you tell them your secret. So validation answers questions like, can I trust this website? Or specifically, is the site being served by the same person who owns the certificate for the site? So this is a form of authentication, verification of identity. How does validation even work? We validate certificates by using the public key infrastructure. Websites have certificates that are authorized by organizations called certificate authorities, or CA in short. The CA authorizes certificates with cryptographic signatures. And your computer has a big list of certificate authorities that it trusts. When a client receives a certificate, it goes through its database of CAs that it trusts, checking if it's signed by any. After that, it can decide that it trusts the website. Except, there may still be something missing. Imagine that Bob's IT person gets a certificate for bobsburgers.com. It's signed by a trusted CA, so it's totally legit, like it's safe and trustable. This IT person goes to Starbucks and sets up a spoof server that redirects, say, gmail.com to their website, to their laptop. And they use bobsburgers.com certificate for the spoof gmail.com site. And your client will say, sure, that looks good. It's signed by a trusted CA from my CA bundle. But, well, fortunately, there's a hostname checking to the rescue. Clients can check that the hostname on the certificate they receive is the same that they requested. This sounds like a straightforward, like obvious check that everyone should be doing, but you'd be surprised. This is an important line of defense against man-in-the-middle attacks. There are also other things that we must check when validating a TLS certificate. Is the certificate past its expiration date? If the certificate was compromised, it can also be revoked, and revocation is a whole different area that I am probably not going to go to today. Okay, something is happening. I'll pause. Okay. Are people able to see it? I'm happy to pause for a minute. Oh, okay. I will pause for a minute.
So this is as good as we're going to get?
Okay. Well, please don't sleep. I'll try to keep you entertained. All right. So yeah, revocation is something we're not going to talk about right now. And that's the authentication or certificate validation part. Next comes the actual encryption. And for the purpose of this talk, let's treat encryption as a black box, something that we don't really need to worry about right now. Instead, let's talk more about TLS. So how does it really work? To do this, I'm going to walk through a TLS session negotiation, or at least like the beginning of it. TLS is really a network protocol, right? So there should be a client and there should be a server involved. The first and the most important thing that about TLS is the handshake. The client tries to establish a connection by sending the server a client hello message. And a lot of stuff follows. The client hello messages contain a list of cipher suites that the client supports. The server responds with a server hello that has the cipher suite it supports, among other things. They exchange information, keys, and other things needed to establish a secure connection. And then a lot of decisions are made. Well, we will come back to look. Well, the question marks in this slide are really important, and we will come back to it soon. Once all these decisions are made, with some magical math and a couple of TLS messages, the switch of encryption is flipped. So, in theory, everything is secure now. Next, I want to talk about two classes, really broad classes of software related to TLS. Let's take a look at how TLS is implemented. Well, this is sort of, I'm just going to list some popular TLS implementations. If I leave something out, it's not because that's a terrible implementation and you should never look at it. It's because I just forgot, maybe. There's OpenSSL, which most servers, non-browser clients use. There's boring SSL, which it's not for everyone. I think Google hasn't guaranteed stable interfaces for it for outside use. There's secure transport for iOS and OS X. There is NSS, there's S-channel for Windows, there's GNU TLS for Linux hippies. And these implementations have a lot of flaws, both in the way that they're implemented and in the APIs that they expose. There's an interesting commonality to all of these, that all the popular implementations of TLS are in C or C++. They've all had bugs caused by memory unsafety. Some of them were big. Heartbleed was one of the examples that I distinctly remember. It was a simple lack of bounds check that allowed attackers to retrieve random data from RAM. It was not a crypto flaw. The encryption magic that I mentioned as a black box was not the cause of this. It was just a classic don't write network code in C moment. A lot of flaws are just plain logic errors in the implementation too, though. Multiple TLS implementations had a bug accepting any certificate as valid if it is signed by a trusted non-CA certificate, even if that certificate is not a certificate authority certificate. For example, bobsburgers.com could sign a rogue certificate for gmail.com and it would be accepted. Okay, now to see who's awake. I will ask all of you to focus on the background text in the slide. This is not some arbitrary C code. It is a basic example of setting up a simple client using OpenSSL. I copied it word for word from their wiki, so I did not even write this myself. Do you see the problem here? The problem is exactly that you don't see it. It's not just a crappy verbose API. It's an unopinionated API. So you have to choose your own settings. Remember the bazillion decisions from the TLS Handshake earlier? Forcing application developers to make these decisions is a bad idea. First of all, it allows them to make bad decisions, and then it prevents applications from being easily migrated to better settings as and when they become available. So this could be so much better, right? And not just implementation flaws. SSL and TLS have a rocky history with backwards compatibility. There are downgrade attacks that allow attackers, usually man-in-the-middle attacks, to prevent a secure connection to be established, which further allows them to take advantage of flaws in the less secure session they've caused. And even though HTTPS is just HTTP on TLS, there are a lot of interesting, unique attack vectors. These are not problems with authentication or cryptography or even implementation or even TLS implementations. These are attacks based on subtle browser behavior. Cookie stealing is an interesting one. The user connects to a secure HTTP website that stores a cookie on their system. So far, so good. The attacker cannot attack this encrypted traffic to the target website, but they wait for you to submit an unencrypted HTTP request to any other website. Then the attacker steps in and responds with a redirect to the target domain, but on port 80. Because any site can issue a redirection to any other site, your browser happily follows. This results in a plain text connection to the target website, which includes all non-secure cookies in your browser's possession. This can be mitigated with the secure flag on cookies, but many developers forget to do that. This exemplifies how tricky securing HTTPS is. It's an extremely complicated combination of factors. And even when the cookies are flagged secure, there's still cookie injection. It uses a similar technique. A non-encryption breaking man in the middle can redirect to target domain on port 80 and send a set cookie header to overwrite arbitrary cookies for that site. Your secure cookies aren't really that resistant to tampering either. And in a lot of cases, the user can be considered a security flaw because they do insecure things, like clicking through certificate warnings. But it's not really the user's fault. We don't prevent them from connecting to sites with invalid certificates. We train them to click through the warnings by just having so many of them. So back to software that uses TLS, we can recall our example from the beginning. Even though this supported TLS, it was used incorrectly, causing huge security holes. It's easy to blame urllib2 or standard library or Python developers or core developers or people who build the language, but I think it's a failing of the industry. If easy, opinionated, secure TLS APIs existed, we wouldn't have had this problem. This is just like the usability problem with browsers, but it's for developers instead. Fortunately, just to say what would have been the ideal case to do here, the request library exists. This gives us an error if the site has a bad certificate. It is, though, sad that urllib2 took so long to be secure by default. Every new Python programmer would probably use urllib2 before they use requests. Well, everyone in the know used requests because it's secure. Well, really because it's easier to use than urllib2, but also secure. But that said, I am sorry that I'm being so negative with all these flaws and attacks. But things are getting better. The first versions of the stock that I gave last year, I wasn't able to say, depending on the version of Python that you're using, this may be insecure. It was outright insecure. It wasn't secure by default. So things are getting better. People are beginning to care. OpenSSL is getting more attention. They're working really hard to make it better. New alternatives are showing up, which means there's hope. But things could still be so much better. Most of these libraries are still implemented in memory unsafe languages. There is a PyCA's cryptography that is a Python project that aims to have opinionated APIs while still exposing low-level primitives when required. So this hides complexity and at the same time exposes it to people who actually want to deal with it. There's PyCA's TLS, which aims to be an easy-to-use and safe TLS 1.2 implementation that I have been building. I've had some really great people contributing to it. I have had some awesome patches. So if any of you awesome people out here are interested, please, please, please contribute. I will make sure that your contributions don't go waste, and it will be much appreciated. with that self-promotion out there. What can we really do for our applications? We can use tools that would tell us how our applications would potentially deal with bad certificates. We could learn more about how to safely and securely configure TLS. We could test our clients against servers with bad certificates to see how those things are dealt with. We can also read and learn more. There is a book called Bulletproof SSL and TLS, which is an excellent example of learning from the mistakes. And there's a book called The Tangled Web, which is pretty well. Which is kind of sad. It tells us about the history of the web and how really we got to this point where everything is broken and sad. But these books are really good weapons to use before we jump in and build something for the internet. I've used a lot of diagrams and stuff from these books in this talk. Also, there is a book called Crypto 101 by my friend LVH, who this book is available free of cost to people, and it is a good introduction to the math part of crypto that I haven't talked much about. But it's really interesting to see how people can, just by providing them with tools that will help them enter the world of crypto, it's interesting to see that it's not that scary and complicated, that only people who have been studying this for years can actually understand what's going on. And I know things can seem scary. I would ask that people be brave, learn, and then help us. We are trying really hard to build a better project around TLS and build a better culture around security. Help us out with the cryptography project. We are really friendly and nice. Well, thank you. We have quite some time for questions, and this is me on Twitter. If you would like to come talk to me later, I will be around at the conference, and I'm also around on IRC in this place, amongst other places. So thank you.
About the Python implementation of the TLS and other Python libraries that you mentioned. What is the goal of these libraries? Are you planning to replace existing C++ implementations like OpenSSL, or what are you trying to achieve? Can you elaborate on that?
Okay, so the question here was the Python implementations of TLS that I mentioned. What is the goal there, and what exactly are we trying to achieve by working on it, right? So thank you for the question. Excellent. The idea behind PyCA's cryptography, which I mentioned initially, is to use the math, the encryption math that OpenSSL implemented, because those should be in C and C++. Those should not be in things like Python. There are wrappers that use those math in Python and implement the things that are not crypto math in Python. So similarly, PyCA's TLS, our TLS implementation that I mentioned, was the idea here is, again, to use cryptography and thus OpenSSL for the crypto math and implement the network protocol part of TLS in Python. The idea is also to provide people with an easy-to-use, friendly API that is opinionated about secure defaults. When I say opinionated, what I mean is that someone who's just learning to write a web application, their first web application, they're really excited about building something and having it work. And it could be really useful. The idea could be really nice, but they shouldn't have to go and read everything there is to know about TLS to make sure that the users of their web application are that their data is secure, that their web application is secure. And the idea is to provide them with an easy-to-use API that would just be secure from the get-go. If you want to go in and change the settings, that is possible, but it shouldn't be something that you have to think really hard about. That is the goal. You're welcome.
Kind of related to that question, in terms of what libraries are used, does cryptography or TLS use the platform features, for example, on the latest release of Hostname Checking? Apple does not ship the headers for OpenSSL deliberately because the version they ship inside is very old, 0.9. So they try to encourage developers to use their libraries. Does cryptography or TLS build these libraries now by default, or does it still require OpenSSL? If you know, of course.
Yeah, I'm trying to repeat the question. So the question here is some of the, well, libraries or vendors out there encourage people to use their own crypto libraries and not depend on things like OpenSSL. They gave an example of Apple, because the version that it uses or ships with are not the latest versions. Did I get that right? Okay, great. First part done. So cryptography, the whole point about being opinionated is, again, making sure that you're not giving the user that many options, and that many options or that much scope to be insecure. As far as I know, they have a list of libraries they're compatible with, but it does require, it does depend a lot, or it does use a lot of things from OpenSSL. That is as far as I know, but it's an active development community, and I am sure like things change every other week. So I don't know what the latest version they're using, but that's the basic idea or basic, let's say, thought behind building this library. And as for TLS, it's still work in progress. We don't do encryption at all at this point. I have just been working on parsing messages that are involved in a TLS handshake. And the most encryption-like thing that we've done has been implementing the pseudo-random function. And that uses cryptography for the hash algorithms, which in turn uses OpenSSL. So that's how the stack works, or that's how they are all related. Does that answer your question?
Yeah, it does answer the question.
Thank you.
Maybe it's a good idea to consider using actually the vendor's library, which seems to be simpler using the latest TLS standards rather than the old.
Well, definitely.
The old OpenSSL.
Well, definitely, it's something to think about. I get the point about like how the compatibility could be an issue, or how it could be very depending on what the latest release of OpenSSL that you support is and what your users want is. And there is a huge like discussion that can go in there. But thank you. Any other questions? No? Okay. Thanks everyone for coming and trying to find a way.